Hello, in this video I'm going to be talking about ionic bonding. We've already covered covalent bonding in a lot of detail, but this video I'm going to show you how covalent bonding and polarity really lead into ionic bonding in a really nice way. And it's all to do with electrons. They're the main thing to understand in ionic bonding, just as they are with covalent bonding. So let's look at a periodic table, which you've all seen by now. So on the periodic table, as we've said, everything on the right of this staircase over here is a non-metal, and everything else is a metal. Except hydrogen, of course, which is a gas, but that's where it fits when it comes time to look at the number of electrons in the valence shell. So everything on this side of the staircase, and the staircase is in red on this periodic table, everything on this side is a metal. So let's get rid of that. Metals all do something very similar, and that is when it comes time to bond with other elements, they lose electrons. And so let's look at a good example. Let's look at lithium, and I'm going to just start with a dot diagram of lithium. So remember, it's in group 1, so it's got 1 electron in this energy level. So 2 on the inner energy level, so that's a total of 3. So that means it's got 3 electrons and 3 protons. So that's the symbol for electron and then the one for proton. So electrons, remember, are negative, and then protons are positive. So, as I've said before, when we talked about covalent bonding, what elements are trying to do is complete the valence shell. They're trying to become like a noble gas. So all the noble gases, helium, neon, all the elements in that final group that are on the right-hand side of the periodic table, all have full shells of electrons, so they don't need to lose or gain or share, so they're completely stable. All the other elements, though, are trying to become stable. So that's why bonding happens. And I've said this before, but bonding explains why you've got millions upon millions of possible combinations of elements from 116 or so, 117 elements. So in the same way you have 26 letters in the English alphabet, millions of different possible combinations of words. So bonding explains all that. So we've looked at the non-metals so far, which has been a really small group. What we're going to do today is look at everything else in the periodic table, and then talk about how the metals bond. So lithium, 3 electrons, 3 protons. So the question that you've got to ask now is, which will happen? Will lithium gain 7 more electrons to complete this shell, or will it lose 1? And the obvious answer is that it's going to lose this 1 electron, which is what happens to all the elements in group 1. So lithium is quite reactive, and all the elements in group 1, as you go down the group, they get more and more reactive. And what they're all trying to do is get rid of that electron. Okay? So if it does that, and I'm going to write atom above here. So remember, the definition of an atom is the smallest particle of an element that can retain the properties of the element. So an atom of lithium has 3 electrons, 3 protons, and neutrons, obviously, some kind of decimal number, just slightly over 3 neutrons. So then, if it loses 1 electron, it still has the same number of protons, but the number of electrons goes down. So the definition of an ion is an element that's lost or gained electrons. And ions have charges, either positive or negative. So metals usually, there are a few exceptions to this rule, but the vast majority always lose electrons. And when they do that, they're trying to complete the valence shell. So obviously lithium had this 1 electron, but it's very difficult to gain 7 more electrons. The easiest thing, and the thing, or the process that takes the least amount of energy, is to lose this 1 electron. So even though it's got a positive charge now, the next energy level down is complete with electrons. So that's more energetically favourable for lithium to exist this way. But it still has the same number of protons, and it still has the same number of neutrons, but lost 1 electron. So the charge on an atom is always zero charge. But for an ion, in this case, if you see how it's got one more positive charge than it does negative charge, it's going to have +1, or a charge of +1. So if lithium lost 2 electrons, it would be +2. And then also, if an element gains an electrons, which non-metals can also gain electrons, which I'll talk about in a second, they would have a negative charge. So when it comes time to show that with an ion of lithium, what we actually write is Li as the symbol plus. So we don't write the 1, just like you don't write x, 1x in algebra to represent x. So this is where we're at so far. Metals, vast majority of elements on the periodic table are metals, and they lose electrons. There is a trend that I'm not going to tell you, it's going to be for you to figure out. If you look at the number of electrons, or the group number that an element is in, it tells you a lot about electron configuration, as we've talked about with non-metals. So that trend still applies. Lithium's in group 1, so 1 electron in its valence shell. So maybe you can start to see a trend with how many electrons it will lose and its group number. Alright, so ionic bonding. So this is what metals do, they lose electrons. So I'll actually erase this. And let's look at a non-metal, so chlorine. So if I just draw the valence shell electrons for chlorine, 2, 4, 6, 7, it's in group 7. So chlorine, there's different options for chlorine. It can share an electron or covalently bond, which we've studied a lot of, or it can gain 1 electron and fill its shell that way. So you might start to notice that if lithium, something like lithium can lose 1 electron and chlorine can gain 1, how these things are starting to come together. So chlorine can gain 1 electron. So it's got 17 electrons, 17 protons. Mr. Walter, do you want to be in the video? Sorry? Do you want to be in the video?
Hello.
Right, you are now. So then, because it gains 1 electron, let's draw it as a dot. It's actually going to have 18 electrons, but still keeps 17 protons. So the charge of the atom would be 0, always 0. But then because it's gained 1 electron, it's going to have 1 more negative charge than positive charge. So it's actually going to have a charge of -1. So if we're going to write the charge of chlorine, we'll write the symbol and then just negative. So rather than write -1, the convention is when writing charges, just write for 1, -1 or +1, you don't write the 1. So think about x in algebra again. So, non-metals generally gain electrons. They can share, but when it comes time to talk about ionic bonding, and if you react a non-metal with a metal, we're talking about ionic bonding exclusively. So in this case, a metal would lose an electron or electrons, and non-metals gain electrons. The number of protons or in the nucleus always stays the same, but gaining 1 electron means a negative charge, losing an electron means a +1 charge, and then obviously if it loses 2, it's got a charge of +2, +3 if it loses 3 electrons, and the same is true for gaining electrons as well. So, let's erase this. So let's imagine you've got an experiment, okay, and you take an element from group 1, so it's got 1 electron in its valence shell. So sodium is the one we're going to use. So an ion of sodium, 1 electron in its valence shell, that's an atom, not an ion. If it loses that 1 electron, it becomes Na+. Same number of protons, but 1 less electron. And if we react it, and if you can actually do this, we can't do it in this room unfortunately, but I'll probably show you a video clip of this on YouTube. But if you take chlorine, 7 electrons in its valence shell, it can gain 1 electron. So if you heat this sodium up, get it nice and hot, and then bubble in some chlorine gas, these things will react and form salt, right? NaCl, table salt. So that's the formula for sodium chloride, which is salt. So this electron, and obviously this is happening on a massive scale, so billions upon trillions upon gazillions of sodium ions are giving their electron to one chlorine. That's happening over and over again, right? Massive scale. So then this electron goes to this outer shell of chlorine. So this becomes Cl minus. And the law of electrostatics, opposites attract, just ask my wife. You've got a positive charge and a negative charge. So these two things attract each other. So the charges cancel out. So you've got a +1 and a -1. Again, with the periodic table, we've started to examine some trends and notice some trends, and there are way more. And as we start to use more of the periodic table, more and more show up. And this is another sort of trend. If you look at any element in group 1, it does this. It gives its electron away. Elements in group 7 gain 1 electron. So that trend of the number of valence shell electrons and the number of bonds it starts to make, there's a very similar trend that I'm not going to tell you. You will figure it out because you're all smart. So a very simple example, but elements in group 1 do this, elements in group 7 do this. Always metals, vast majority of cases, I can almost say always, metals lose, non-metals gain. Non-metals can also share electrons in covalent bonding, but not when you've got a metal that it's being reacted with. So that's a nice and simple sort of case. Let's start to maybe look at a more complex version. So let's look at oxygen this time. So oxygen is in group 6, so it's got 6 valence electrons. Right, so it's 6 valence electrons, but it's got an atomic number of 8, so that's 8 electrons, 8 protons. And so it needs to gain 2 more. And it can either do that by sharing, covalent bonding, or gaining 2 from a metal, ionic bonding. So it's going to gain 2 electrons. So this is the atom. Should have kept that writing up there. So if it gains 2, it'll have 10 electrons and 8 protons. So the charge is going to be -2, because it's got 2 more negative charges than positive charges. So let's say it reacts with sodium. So sodium's in group 1, gives this electron to the oxygen. So because you've got massive quantities of these and these, you've got to get another sodium to give its other electron. So it'd be really nice if it was just a ratio of 1 to 1 all the time. It doesn't quite work that way, but it's actually pretty simple to understand. You need 2 of these for every 1 of these because you need 2 electrons. Sodium's not going to break a shell that's full. So if it loses this 1 electron, the next shell down is going to be left alone, right? It's not going to react. It's completely full, more stable. So you need 2 atoms of sodium to get 2 electrons to this oxygen. Obviously sodium, this is +1 and +1. So the short way of saying all this is, if I've got -2 for oxygen, I need 2 pluses to make this a neutral substance. So we will start to look at formulas, and this is a formula, why we actually get this. There's another way to figure this out. And I'll actually introduce it in a second. But if you know that oxygen's in group 6, it needs to gain 2 electrons, right? So you need 2 sodiums for that to happen. So this represents, for every 2 sodiums, they give 1 electron each to get the 2 electrons to sodium. To oxygen, sorry. So I'm going to show you another way to figure that out. So for this, we need to talk about Fu. What does Fu stand for, Mr. Slater? Well, it stands for a lot of things, but in this case, it's going to stand for formula unit. So Fu. So rather than talk about a molecule, And the definition of a molecule, we need a different way to describe an ionic compound. And ionic compounds are usually solids. So, and we'll talk about why that is in a second. So we're going to talk about formula units. So how do you write the formula for a formula unit? Well, you know, and you'll start to get this. The more you do this, the more you practice, the easier it'll become, and you'll actually see the trend right away. But sodium always makes a +1 ion. Oxygen always makes a 2- ion. Yeah, 2-. And so the quick way to look at this formula or these two ions and figure out the formula is to do something called crisscross, which was a very cheesy band from the early 90s, rap band. Anyway, so the ratio is 2 of these for every 1 of these. And the quick way of doing that is to bring this 2 down here and this 1 down here, but we don't write the 1 like algebra, you don't write 1x. So this is crisscross. So if you're trying to figure out the formula of an ionic compound, this is one method. Bring the numbers to the opposite position, and it gives you the formula automatically. But you might just look at it and go, all right, so for every 1 of these, or for every 1 of these, I need 2 of these. So if you see that, then that's great. But if you're struggling, or if it's not as easy to see that, then just bring the numbers to the opposite place. Right, so then, as well as formula units, we describe this is a formula unit. Like something like H2O would be a molecule because it's non-metal. And there's a reason why we call it a formula unit, which I'll talk about next. So the big idea with crisscross is one way to figure out the formula. It's not the only way, but it's just a good rule to follow. So why is it that we call ionic solids formula units? Well, if you think about sodium chloride, if you take a sample of sodium chloride, it looks like small white crystals. And what you actually have in an ionic solid is lots of these things, right? Sodium and chloride ions. And so because of that, you can actually attract a chlorine up here, a chlorine down here, a chlorine over here, a chlorine behind the sodium, and then a chlorine in front. So around every sodium you can get 6 chloride ions. And so then if you imagine that as that pattern continues, around every of these chloride ions you can get more sodiums. And this repeats all the way through an ionic solid. So you don't have discrete molecules like H2O. I'm sorry, let me redraw that. Attracting other molecules. So these bonds are nowhere near as strong as these. These are actually delta charges, remember, from covalent bonding. So this isn't as strong as an attraction as between a full positive charge and a full negative charge. So really, when we look about FUs, what we're really looking at is, well, what's the formula of just one unit of sodium chloride? Because in a sample of an ionic solid like sodium chloride, you've got loads of these things. And remember that for every 1 sodium, you've got 6 chlorides around it. And then it starts to get really kind of mind-blowing because around all of those, you've got 6 other ions, all attracting each other really strongly. And so we talk about just one unit, and it's a formula unit. And they use the crisscross method to do that. So if we were looking at sodium chloride, it's just NaCl. Because there's no numbers here, so it's 1 to 1. And so sodium ionic solids like sodium chloride have really high melting points. They're really difficult. I don't think we have the ability to get the temperature high enough to melt a solid like this. It is possible, but you need very high temperatures, which we can't do. I think it's hundreds and hundreds, like 500 or 600 degrees centigrade to actually make this a liquid. And it's because of this strong attraction, electrostatic attraction between all the different ions. So, as I mentioned earlier on, what we're going to do is actually show how covalent bonding, delta charges and polarity leads into ionic bonding. And it's actually pretty cool. So I'm going to get rid of this. Okay. So the scale for polarity, when you subtract electronegativity values, if it's between 0 and 4, oh wow. 0 and 3.9 is non-polar, 0.4 is polar, still covalent at that point, and if it's over 2.0, it's ionic. We'll do this activity in class, but we'll actually subtract some negativity values just so that you can see that generally, and there are a few exceptions, there always is, when you subtract electronegativity values for ionic compounds like, say, sodium chloride, the value that you'll get will be 2.0 or over. So we talked about covalent bonding. So the idea of polarity and covalent bonding is that not all electrons are shared equally. Chlorine's pulling on these electrons more, so it has a delta negative charge. As we get into ionic bonding, it's really it's going beyond sharing. It's about stealing. So hydrogen would actually, in an ionic compound, like let's do an NAF. The fluorine would actually take the electron. They wouldn't share. It's gone on the scale. It's gone beyond sharing. It's more stealing. So the sodium electron would be stolen by the fluoride. So this is what we've been doing, and we're actually here now. We're looking at stealing electrons and taking, having electrons stolen. So giving and receiving electrons is where we're at.